Hi together! In this video you will hear about a flexible approach to modeling item position effects within the framework of Bayesian item response theory, even when the sample structure is complex, such as is common in large-scale assessments, for instance. My name is Matthias Trentl and I'm working at the Center for Research on Education and School Development at Dortmund University in Germany. I am very pleased to have the opportunity at this mini-conference at the Stanford Graduate School of Education to present parts of my research, which in this case I'm conducting together with my dear friend and colleague Alexander Robic. This presentation summarizes the main ideas and results that we have previously published in the Journal of Educational and Behavioral Statistics, which can be found at this link. What can you expect here in the next couple of minutes? I will briefly introduce item position effects within cognitive tests and give a rationale for why we did what we did, followed by the presentation of the actual model we are proposing and using, and I'll explain its main features. I will talk a little bit about how we estimate its parameters, and to see how our approach can be applied to empirical data, we analyzed data from the PISA study, and I will show you what we found there. Finally, I will discuss some limitations of the model along with some ideas on how the model could be extended. So let's go. What do we know about item position effects so far? Generally, on average, one can usually see a change in performance on cognitive tests with increasing test length. Often, this is a drop or a decline in performance. However, performance increases are sometimes also possibly observed when, for instance, there's something like a training effect during a test. These changes, whether decline or increase in test performance within a test, are often referred to as item position effects. That such item position effects occur has been demonstrated in numerous studies, including large-scale assessments such as PISA. In addition to a general position effect averaged across individuals, it was also shown that individuals also differ among each other with respect to this effect. To account for this, these individual differences are often modeled with another person dimension, often called test persistence. For both the overall change in performance as well as the individual deviations from this are modeled mainly using an assumption of linearity, which essentially means that these changes happen in form of a linear curve. However, we also know from other studies that this linear course of item position effects does not always seem plausible. Then sometimes another functional relation is suggested, a quadratic or a cubic relation between effect and position, for instance, which is also not always plausible, which leads us to our research interest. Our research aim can essentially be described in terms of three requirements for the model and its estimation. First, what we wanted to do is to build on already established item response models to develop a much more flexible model to study item position effects that makes as few assumptions as possible about how effect and the actual position of the corresponding item are related. Second, regarding the estimation of the model parameters, we also wanted to keep as many degrees of freedom as possible, and therefore we decided to use a Bayesian estimation procedure in order to be able to extend and estimate the model for more specific problems. I will go into this in a little more detail in the discussion section. And third, since we are often confronted with complex sample structures in large-scale assessments, and our approach should explicitly also be suitable for this kind of data, our approach should also be able to adequately account for these sample structures. In the following, I would like to outline how we tackle these three challenges. Let me start with the actual model we proposed to examine these effects of item position. Before I walk you through the model step by step, I will clarify some notations. I assume n individuals indexed by lowercase p responding to I items indexed by lowercase I, and t block positions indexed by lowercase t. Block positions because most test designs used for cognitive tests and educational assessments, in particular in large-scale assessments, are assembled in the form of a block design. This means that an item is assigned to exactly one block consisting of several items, and a test booklet then consists of several blocks, which means that an item can occur only in as many positions as there are blocks in a booklet. Normally, an item is always in the same position within its block. A block, on the other hand, occurs in different positions in different test booklets. Probably the most common block design is the balanced incomplete block design. Given this notation, we start with a simple 2 parameters response model written as a generalized linear mixed model. To link the expected response, which is in the binary case the probability of success on the left side, to the linear component on the right side of the equation, we use the probit link as a link function. This is for the simple reason that the probit link makes it much more convenient for us to derive the Bayesian estimation procedure later on. But of course, other link functions like the logit link could theoretically be used. The parameter theta represents the person ability specified as a random effect with respective item-specific loading parameters A, and the parameter B represents the item-specific intercept, which can be interpreted as item difficulty. In the next step, we introduce a general difficulty shift beta for position T. This represents the amount of mean change in difficulty across all individuals when considering position T. Now we model the test persistence eta, which allows for individual deviations from this shift beta on the person side as a second random effect, and give this factor a position-specific loading parameter gamma for position T. This means that on the one hand, persons can deviate to different degrees from the mean difficulty shift beta, and on the other hand, this factor can have a varying influence on the person's performance depending on position T. Furthermore, we believe that the influence of persistence on performance may differ between items, and therefore we add an item-specific loading parameter alpha to this term. Overall, this results in a two-dimensional response model with person dimensions theta and eta, ability and persistence, assumed to be bivariate, normally distributed with mean value 0. The main innovation in this model is that we do not make any assumptions of how the position effects are related to the single positions T. They are completely free and are not restricted to a pre-specified form, such as a linear function, for instance. This model, however, is highly parameterized, and we should check under which conditions and restrictions this model is identifiable. The first restriction concerns the bivariate normal distribution of person factors. Here we have to fix the variance to 1. This is not surprising, and we know this from other 2PL models. The second restriction concerns the first block position. Here we set both the beta shift parameter and the gamma parameter to 0. Thus we assume that no position effects occur on the first position. For the shift parameter beta, the first block position serves as a reference position, and the beta parameters of the other positions are to be considered in comparison to this reference position. For the person factor eta, this means that the test persistence on the first block position has no influence on the test performance. The third and last restriction of the parameterization concerns the block position 2. Here we set gamma equal to 1. Thus, on the one hand, this position serves as a reference position for the gamma parameters. On the other hand, the variance explained by the factor eta on this position is reflected in the item-specific loading parameters alpha. In addition to these restrictions on parameterization, we will still have to make a few demands on the properties of the data. We do this by requiring certain properties of the booklet design. First, we require that a test booklet has to be composed of more than 2 blocks and that one block contain more than one item. This is basically to ensure that non-restricted block-specific parameters can be modeled meaningfully at all. Second, for each item we need at least 2 blocks in a way that this item appears on block position 1 and block position 2. With this, we can more or less identify the loading structure. And third, for each block position t greater than 1, there must be a booklet containing a pair of items such that one item is administered on block position 1 and the other item is administered on block position t. This is basically so the shift parameter beta can be identified. If these requirements are met, one can show that the model is identifiable, and if anyone is interested, I would refer to our article where we have given a full proof of that. These test design requirements are very often met in educational assessments, but sometimes they are not. If not all conditions are met, one can obtain identifiability through appropriate further restrictions on the parameterization. Now we know that the model is identifiable, at least under certain conditions, and thus the parameters can be interpreted in a meaningful way. Therefore, I would like to go on and say a few words about how to estimate them. First, I would like to note that this model is in principle also estimable with maximum likelihood method, such as the EM algorithm. However, we have chosen a Bayesian approach in order to retain the flexibility to extend the model to cross-classified models in order to investigate, for example, item covariates with respect to item position effects. When we consider the item parameter vector delta, in Bayesian terminology, the posterior distribution can be viewed as a term consisting essentially of the product of the likelihood part and the prior part. Since such a high-dimensional posterior distribution is difficult to determine, often a component-wise sampling is applied, and we did this in the form of a Gibbs sampler. From this sample, the so-called expected a posteriori can be estimated, which then serves as a consistent estimator for our parameters. This is not very exciting and a rather standard Bayesian procedure so far. What is also standard in educational assessments is that we are usually faced with complex sample structures. In order to avoid any resulting bias, but also to circumvent problems that may occur with regard to inference, usually sampling weights are used combined with certain resampling methods for the derivation of correct standard errors. This is a standard procedure in frequentist statistics, but not yet really widespread in the Bayesian context. However, we wanted to do this for our Bayesian analysis. In order to take sampling weights into account in the Bayesian, only the likelihood part has to be modified by weighting the likelihood components with respective sampling weights. What results is also referred to as the so-called pseudo-likelihood. So we take this pseudo-likelihood and plug it in to derive the posterior distribution and obtain a weighted version of our EAP estimator. Now, to compute standard errors for this estimator, we make use of the usual resampling methods. These methods are usually based on replications of the sample with sample weights adjusted appropriately for each replication. For each of these replications, the estimator is then recalculated based on the adjusted sample weights. The covariance matrix is then derived from the deviations of these replication-based estimators from the original estimator. Typically, a scaling factor is applied depending on the replication design and the number of replications. For example, PISA uses a balanced repeated replication design with 80 replications. This results in a scaling factor of 0.05. This also means that you have to estimate the model 81 times, once with the original weighting and 80 times with the correspondingly adjusted replication weights. The literature also discusses methods for adequately accounting for sample structure in model comparisons. Lumley, for example, introduces a design-based AIC as an information criterion that does not penalize the pure number of model parameters, but adjusts this number with a design effect. For data leading to higher design effects, the number of parameters is penalized higher than for lower design effects. To calculate this design effect, we need on the one hand the covariance matrix of the parameter estimators, which we already have, and on the other hand a weighted version of the Fisher information matrix, which can also be calculated numerically or approximated. This gives us all the math we need to estimate our model in the presence of complex sampling structures, to make inferential statistical statements about the parameters, and to perform model comparisons. We have implemented all the computational algorithms in R, and we have also presented the main code passages in our paper in the supplemental material. Now let's see how our model can be applied to empirical data. For the empirical example, we looked at data from the PISA 2000 wave, specifically from the reading domain. We picked a country at random, in this case New Zealand. So we look at data from a total of 2,853 15-year-old students from New Zealand. For these students, we have data on 96 reading items, where we have dichotomously coded all items. We scored missing values due to both omitted and not reached as false responses. The test design used in this study, which is displayed with the table on the right side, needs a little further explanation. Reading was the main domain at that time. This was reflected in the test design in such a way that 7 of the total of 9 test booklets used had purely reading blocks in block positions 1, 2, and 3, and either math or science was administered in the last block position. The first half of the test booklets 8 and 9 contained math and science items, while the second half contained reading items. The link between these two groups of test booklets, however, was only realized using only a single block R8, which also only appeared on the last 2 block positions and not on front positions. Therefore, we decided to look at a sub-design, namely only the first 7 test booklets and also only the responses of the first 3 block positions. This sub-design provides data in a way that our proposed model is also identifiable. The sub-design we consider is shown in black in this table, and the parts we do not consider are grayed out. So we only consider the first 3 block positions, and if we look at the averaged success rates per block position in the table at the bottom left, we find that from position 1 to 2 there is a drop in the average performance, and from position 2 to 3 there's an increase again. 2 comments. First, in the 2000 wave, a 15-minute pause was administered between block position 2 and 3, which could at least partly account for this increase in mean performance. In later waves, by the way, this pause was shortened to 5 minutes. Second, the descriptives already show that a linear course of position effects cannot always be assumed, especially not here. To see how our model performs on empirical data, we estimated the model in its unrestricted version in a first step, and in a second step we tried different restricted versions. The model M1 is the unrestricted version. It is the most flexible model. Model M2 represents the model that assumes a linear progression or course of position effects. In addition to this, we have also investigated a model M2b, which assumes a constant position effect from position 2. In model M3, all loading parameters are fixed at 1 to see what effects the flexible loading structure can have. In model M4, we omit the second person dimension, the persistence, and model only the average shifts for each position in a one-dimensional response model. We estimated each model with our proposed Gibbs sample at a burn-in phase of 25,000 and a total chain length of 50,000. We checked the convergence properties using the usual criteria and found no peculiarities. So the posteriors seem to have been well obtained. So what are the results? This table summarizes the main results of the model estimates. The first 3 columns describe the mean values of the item-specific parameters. Note here that we fixed the variances on the person side to 1, and thus these variances are reflected in the item-specific loading parameters. Thus, the mean of the A parameters and the mean of the alpha parameters can be considered as a kind of a proxy for the standard deviations of theta and eta respectively. That is, to approximate standardized values, one has to set the corresponding effects in relation to the mean of the A parameters. For model M3, however, the values in column 1 and 2 are the actual values of the standard deviations, since here we have fixed the loading parameters to 1 and the standard deviations were estimated freely. Let's go to the other side of the table. The last two columns show the difficulty shifts beta for position 2 and 3. Remember, this parameter is fixed to 0 for the first position. Here we see that all models that make no assumption about the course of position effects, namely models M1, M3 and M4, map what we have already seen in the descriptives also into the corresponding shift parameter. On the last position, there seems to be no significant differences between these models either. On position 2, however, there are differences. And this is probably due to the second person dimension. This should become clearer if you look at the gamma parameter for the third position. Remember, for the second position, it is fixed at 1. The gamma parameter for the third position, when estimated, turned out to be very small. This means that the persistence on the second position contributes quite a bit to the variance. For models M1 and M3, it contributes about half of the variance compared to the ability. On position 3, however, it contributes almost nothing. Consequently, the effect of the different loading structures can be seen for position 2, but not for position 3. For the models which postulate the form of the course of the position effects M2 and M2b, the expected results came out regarding the shift parameters. The shift is underestimated for position 2 to a greater or lesser extent and overestimated for position 3 accordingly. If you look at the correlation between the Pearson factors, they are positive in all models, with the highest amount for model M1. This is the model with the highest flexibility regarding the loading structure. Finally, considering all parameter estimators together, we find that model M2b seems not so dissimilar to model M1. And this is also reflected in the results of the model comparison. Here, model M1 is the best model according to the design-based AIC, but closely followed by model M2b, which has the smallest design effect among all models. Model M2, the model that makes the linearity assumption, performs worst among the considered models. Between them land the models M3 and M4. Let's summarize and discuss things. What I have presented here is a very flexible model for modeling item position effects. Why is that? Well, on the one hand, it does not require any assumptions regarding the course of item position effects, and on the other hand, it can be extended relatively easily by the Bayesian approach, whereby data from complex samples can also be analyzed. However, I have to make some restrictions, of course. For example, so far the algorithm is only implemented for binary data, and usually in educational assessments also polytonously coded data have to be processed. So we still have some work to do here. Another limitation is the assumption of a bivariate normal distribution on the Pearson side. In principle, other distribution forms are also possible. In particular, those that only allow positive values for persistence should be considered here. Which brings me to the outlook. In the near future, an algorithm should be available that can also process polytonously coded data, implementing Metropolis-Hastings steps. Furthermore, we would like to allow even more dimensions so that it's possible to analyze position effects simultaneously with several ability dimensions for tests with more content domains, as it is the case with PISA, for example. And the last thing I would like to mention here is that we would like to extend the model to include random effects on the item side as well, to also examine item covariates and to what extent these are related to position effects. That's all from me. For those who want to read it in more detail, I recommend our article published by the Journal of Educational and Behavioral Statistics. And of course, if there are any questions, suggestions, or the like, I'm always happy about any message. The best way to reach me is via the email address shown here. Thanks for watching and happy modeling!